And we just proved that if we are trying to calculate GCD of two numbers, we can also subtract one from one side and then calculate GCD and we'll get the same answer. So here's a bonus of seeing what does this get us. So here's a bonus example. Suppose I'm trying to calculate GCD of 242 and let's say 55. Now I could write out their factors and look for common factors and things of that sort, but I could also say, wait, this is by the theorem above, this is equal to GCD of 242 minus 55, comma 55. Now I can work with smaller numbers, and I can use this theorem several times to subtract multiples of 55, right? If I subtract 55 and then 55 again and again and again, it should still work. So let me subtract 4 times 55. So I will use the theorem above 3 more times for a total of 4 times. Then 4 times 55, oh, what is that? Let me write it over here. 50 times 55 times 4, 220. All right, so then GCD of 242 minus 220, that's 22 comma 55. And at this point, I think I can guess the common factor now. It's 11. 11 times 2 and 11 times 5. But we can streamline this process, and this is called Euclid's algorithm. This is discovered so long ago, and it's a very fast algorithm for calculating greatest common divisor. You can prove that this is actually faster than factoring and trying and so forth. So what we would do is start with 242 and then write and divide by 55 and then use the division algorithm. So if you know how to divide by something, and you will get a quotient and a remainder. The the division algorithm says that if you have two numbers a and b is greater than 0, then you can divide a by b and get a quotient q and a remainder r, and the remainder should be between 0 and b. This is something you know from kindergarten, and you know it to be intuitively true. This is a theorem that we could actually prove. Now let's leverage that. So if you're dividing, what are we trying to divide here? We're trying to divide 242 by 55. Then the division algorithm says that we can rewrite that. There's a unique way. In fact, this says unique. So there's a unique way to write this as quotient. So 4 plus 22. And then we can bring this 55 over to this side and then bring the 22 over here and then keep dividing. So if 55 divided by 22, the quotient is 2 and the remainder is 11. And we will keep going like that. So bring the 22 over here and then bring the 11 over here. 22 divided by 11, the quotient is 2 and then the remainder is 0. And when we reach 0, we can go back up one level, and that is our GCD. And this works because if you trace this through, the first line, the calculation we're trying to do is saying, hey, I want to calculate the GCD of 242 and 55, but equivalently, we can subtract 55 several times, and that's this calculation doing it for us, so that eventually we get to 22. So that would be this 22, right? So instead of calculating GCD of 242 and 55, we can calculate GCD of 55 and 22. And then we can also flip this around, and then so use the same process again. Instead of calculating GCD of 55 and 22, we can subtract 22 from 55 a few times to get even smaller numbers. For example, here we eventually get 11. So instead of calculating GCD of 5522, we are calculating GCD of subtracting 22 a few times. And so then that's GCD of 11, 22, using the theorem that we proved up here, that we can subtract it once. Well, we can subtract it many times. And then so we get GCD 11, 22. And technically what we did here is that we tried it one more time. So we flipped the order and then tried to subtract. And this time, after subtracting 2 times 11, again using the theorem we proved 2 more times, then we get GCD of 0, 11. And remember from the beginning of the video, we say that GCD of 0 with anything is that same thing. So once we get here, we know that this is 11, and that's our final answer. And we see that from these equations right here. So Euclid's algorithm allow us to continue to divide numbers and then get the numbers smaller and smaller until the GCD pops out at us. So that's it for today. Bye.